Let us now discuss columns or compression members. Column is a compression member that is so slender compared to its length that under gradually increasing load, it will fail by buckling. And these buckling loads would be considerably less than those required to cause failure by crushing. So, if we have got a column and that is subjected to some loading, this second figure shows buckling of a column. Therefore, the buckling failure differs from the compression failure. In the buckling failure, we have the column undergoing lateral deflection. Thus, there is a cutoff length above which the column will buckle. Below that cutoff length, the column would fail by crushing. Although there is no sharp line of demarcation between short compression members and columns, a compression member is generally considered to be column when its unsupported length is more than 10 times its least lateral dimensions. Columns are usually subdivided into two groups. One is long column and another one is intermediate column. Rarely the short compression block is considered to be a third group. The distinction between the long, intermediate, and short column is determined by their behavior. Long column fail by buckling or excessive lateral bending. Intermediate columns fail by combination of crushing and buckling, whereas the short compression blocks fail by crushing. An ideal column is assumed to be a homogeneous member of constant cross section that is initially straight and is subjected to axial compressive loads. Nevertheless, columns would have some small imperfections of material and fabrication irregularities, as well as unavoidable accidental eccentricities of loads. All these factors produces an effect which is shown highly exaggerated in this figure. So we have accidental eccentricity. We might have a center line of the column which is not straight, or in other words, which is crooked, and there can be some fabrication errors in the column. The initial crookedness of the column together with the placement of the load causes an indeterminate eccentricity with respect to the centroid of a typical section, which is shown as an MN section in this figure. If the eccentricity is relatively small and the member is short, then the lateral deflection is negligible and the flexure stress is insignificant as compared to the direct compressive stress. However, in case of a long column, which is normally flexible because of the deflection at a relatively low value of load P, may cause a large flexure stress accompanied by negligible compressive stress. Hence, there are two extremes. One extreme is that a short column carries principally a direct compressive stress, and the other is long column, which is subjected primarily to flexure stresses. As the length of the column increases, the importance of direct compressive stress decreases, and that of the flexure stress increases. Unfortunately, the intermediate column range is not possible to determine the rate of change in these stresses or the proportion of each stress that constitute the resultant stress. It is this indeterminateness that give rise to many formulas in the case of intermediate columns, and many code of practices address these formulas. In the following discussion, we will first of all discuss beam deflections. After that, we will discuss the critical load, and finally, we will derive a long column formula by Euler and work out some examples. Let us first discuss beam deflections. Beam Deflection refers to the bending or curvature of a beam under the influence of external loads. If we have got a beam subjected to some external loads, after the application of the load, this beam will assume a curvature and it will undergo deformation, resulting in change of shape. So in this figure, before application of the load, the beam was straight, and after application of the load, it has deflected. The edge view of the neutral axis or the edge view of the neutral surface of a deflected beam is called the elastic curve of the beam. In mechanics or structure analysis, we normally are interested in determining the equation of this curve, which helps us to find out the vertical displacement y of any point in terms of its x coordinate. We normally consider the left end of the beam as the origin of an x-axis directed along the original undeflected shape of the beam or undeflected position of the beam, and a y-axis directed positive upward. In deriving an equation of this curve, it is assumed that the deflections are so small that there is no appreciable difference between the original length of the beam and the projection of its deflected length. As a result, the elastic curve is very flat and its slope at any point is very small. The value of the slope at any point of this curve can be taken as tangent theta is equal to dy by dx. In this figure, we have taken a piece out of this beam which is subjected to some arbitrary loading, and within that piece we take 2 points which are very close to one another, or in other words which are ds apart, and we draw normal to the tangents drawn at these 2 points. These normals would meet at a point provided the beam has deflected. So the point where these normals meet, keeping that as center, we can draw a circle which touches the 2 point of interest and all the points which come in between these 2 points. That circle is called circle of curvature, and the radius of that circle is called radius of curvature. Now, as we said that if we draw tangent at these 2 points of interest, the change of angle between them would be very small, since we have considered the elastic curve to be almost flat. Therefore, d theta is the small differential change of angle between the tangent at the 2 points which are very close to one another. And these 2 points lie on the elastic curve. In order to ease our reference to these 2 points, we shall call them point A and point B. So point A is closer to the origin as compared to point B. A tangent drawn at point A is assumed to make an angle theta with the original position of the beam neutral surface, which is the straight line. Therefore, this tangent is shown as making angle theta with the horizontal axis in this figure. Since we have considered the slope to be very low, tangent theta can be written approximately equal to theta. So theta is equal to dy by dx. Now we can differentiate both sides of this equation with respect to dx. That will give us d theta by dx equal to d2y by dx square. Please note that y gives the vertical displacement at any point in terms of x coordinate. Since AB can be considered as part of a sector, we can write ds, which is the arc length between A, B, equal to rho d theta. Therefore, ds is equal to rho d theta is written over here. Now we can take rho to the left side and bring ds to the right side, and that gives us 1 by rho is equal to d theta by ds. And that can be considered approximately equal to d theta by dx. So this arc length can be considered equal to dx if the slope of the elastic curve is very small. Thus, we will get 1 by rho equal to d2y by dx square. Now, from our previous discussion of flexure stresses, we derived that E by rho E is equal to m by I is equal to sigma 3 by x2. Thus, from this ratio, 1 by rho is equal to m over EI. And plugging the values, we get m equal to EI d2y by dx square. EI is called flexure rigidity of the beam. The reason we have discussed the beam deflection in our presentation about the compression members is that we will be trying to derive the equation for long columns, and long columns can buckle. In other words, the long columns have tendency to deflect as shown over here. So therefore, this equation will be used later to derive Euler equation for long columns. Now let us discuss critical load. Critical load is that load at which a column would buckle. Whenever a member is designed, it is necessary that it satisfy strength, deflection, and stability requirements. We discussed that if the members are long and slender, they are susceptible to buckling. Buckling is the lateral deflection of columns. Buckling of columns can result in sudden and dramatic failure of structures or mechanisms, and special attention must be given to the design of columns so that they can safely support their intended loading without buckling. Therefore, it is very important to consider the critical load at which the column would be on the verge of buckling. The critical load, often referred to as P with subscript CR, can be worked out by considering the column in this figure. This figure shows a column which is subjected to load P, and at point A, which is at the middle of the column, we have introduced a restraint. The spring shown in this figure is a helpful tool for determining the lateral deflection of this column. It will also give us the proportion of the load required in the horizontal direction to provide lateral deflection. Please note, when the two bars are in the vertical position, the horizontal spring having stiffness K is unstretched. We apply a vertical load P and keep on increasing the magnitude of the load P to an extent that the column start deflecting laterally. Once the column starts deflecting laterally, the spring will induce a restoring force F is equal to K times delta on the column. On the other hand, the applied load P will develop a horizontal force of P tangent theta. So at point A, we would have a load P, the restoring force F of the column, and another load P induced by this lower vertical bar, because that P is resulting from the equilibrium of joint A. As we can see that the top bar has bent by an angle theta, or in other words has deflected by an angle theta. So obviously there is a proportion of the load P running in the top bar. The remaining load will induce horizontal buckling. Therefore, the applied load P at point A has been decomposed into two loads, one horizontal, which is P tan theta, and one in the direction of the top bar. Using triangular law of forces, the oblique component and the horizontal component should add up to the vertical applied load. The same thing will happen in the case of lower bar. This applied load P will be resisted at the bottom, and similarly we will have load P contributed by the bottom bar. Hence, the applied load P develops two horizontal components, Px equal to P tan theta, which tend to push the pin further out of the equilibrium. Now, theta is considered small, so we can get the horizontal deflection delta equal to theta times L by 2. Because of small magnitude of theta, we have considered tangent theta is approximately equal to theta. Therefore, delta is approximately equal to theta times L by 2. This makes F, which is equal to K theta L by 2, equal to 2 times P theta. Hence, if the restoring force is bigger than 2 times P theta, then that will be called as stable equilibrium. On the other hand, if K theta L by 2 is less than 2 times P theta, then that condition would be called as unstable equilibrium. From this, we can write that P critical is equal to KL by 4. So instead of greater than or less than, if we equate these two equations, we will get P critical is equal to KL by 4. Now let us derive an equation for long columns. A theoretical analysis of critical load for long columns was made by a Swiss mathematician called Leonhard Euler. His analysis is based on the differential equation of elastic curve which we derived earlier. This differential equation is EI d2y by dx square is equal to m. In order to derive the Euler's formula, let us consider a column whose top end is considered to be at origin O, horizontal is considered as y, vertical axis is considered x. Load P is applied at the top and correspondingly there will be load P at the bottom of the column. We assume that the column has deflected horizontally by delta. Thus, we can write EI d2y by dx square is equal to m. This is the same equation which we derived earlier, and this m is equal to p times minus y. The reason we are taking y minus is the deflection of the column is in the negative y direction. Now this is the second order differential equation and its solution is equal to C1 sine x under root p over ei plus C2 cos x. In order to work out the constants C1 and C2, we can substitute at y is equal to 0, x is 0, as we can see from our column. Plugging the values will give us C2 equal to 0. Similarly, at y is equal to 0, at x is equal to L, and that will give us C1 either equal to 0, in which case there won't be any bending of the column, or equal to L times square root p over ei equal to n pi, where n is equal to 1, 2, 3, and so on. From this, we can square both sides and bring the terms to the right hand side and get our P critical equal to n square EI pi square by L square. Please note that the value of n is equal to 0 is of no concern to us. It will give us a trivial solution, meaning that the load is equal to 0. For the other values of n, the column bends in different shapes, and these shapes are shown in this figure. If n is equal to 1, the column bend in one shape. However, if n is equal to 2, then the column bend in two shapes. Similarly, in case of n is equal to 3, the column bends in three shapes. This is equivalent of saying that in case of n is equal to 2, the column is restrained at the midpoint. In case of n is equal to 3, we have 2 points restrained between the height of the column. In this first example, it is important to notice that we have considered the n or the boundary condition as pinned. That's why we have got a deflected profile which is parabolic, and the whole length has deflected. If we consider another end condition, for example, which is both end fixed, then our column would bend in this shape. For this, we don't have to do much. We just can adjust our Euler equation. Since we know that P critical is n square EI pi square by L square, this L in the case of pinned section was the full height of the column. In case of both end restraint, we can reduce that L to L by 2. In a similar manner, we can derive the critical load equation by changing the length. Therefore, we call this length as an effective length. So in the case of both end hinged, our effective length is L. In the case of fixed ends, our effective length become 0.5 L. In case of one end fixed and other hinged, our effective length becomes 0.7 L. And finally, when one end is fixed and the other is free, our effective length becomes 2L. The effective lengths are also shown pictorially in these figures. Now, as we know that the Euler formula, which we developed earlier, is for columns having ends that are pinned. In other words, the effective length for the pinned column is L. In the case of other end conditions, such as one end free and another end fixed, we can put effective length equal to 2L in our Euler equation and get the critical load. Similarly, in the case of both end fixed, we can put effective length equal to 0.5L. And for a pinned and fixed end, we can put effective length equal to 0.7L in our Euler buckling load equation. Now, one important thing to realize over here is that in the case of pin end, we have a curving out profile of the column. In the case of other end conditions, we are trying to achieve the curving out profile of the column. So for fixed and free ends, the deflected profile is half of the profile of pinned ends. So therefore, we complete our convex profile by putting effective length equal to 2L. So if we draw a mirror image of this profile, we will get the same curving out profile as in the case of pin end. In the case of fixed end, because of the end restraint, the curving out profile has shrunk, and therefore our effective length reduces to 0.5L. In the case of fixed and pinned, our curving out profile is 0.7L. In the same way, this curving out profile is between 2 points, which are called point of inflection. So in case of fixed end, the inflection points is at 0.5L, and from there the curve starts changing its curvature. Similarly, in the case of pinned and fixed end, the point of contraflexure or inflection point is at 0.7L from the top pin support, and we can see that the curve is starting to change its curvature after the inflection point. Now we will discuss limitation of Euler formula. Euler formula gives us the buckling load, which is pre-critical equal to n square ei pi square by le square. One important thing to observe is that the critical load for a cross section having minimum I will be the controlling load. In other words, if we have a cross section like a rectangular cross section, the moment of inertia in one of the direction will be bigger than the moment of inertia in another direction. So I y will be smaller than the ix. Hence, the column has got tendency to buckle in the least moment of inertia direction, which is yy. So that can be clearly seen from this equation. Another important factor on which the Euler formula is dependent is the strength of material. So a material which is having higher modulus of elasticity will give us a higher critical load, and a material having lower modulus of elasticity will give us lower critical load. Another important information that can be got from Euler formula is the slenderness ratio. So if we divide our both sides by A and write our moment of inertia in terms of AR square, where R is the least radius of gyration, we can get the equation P by A is equal to E pi square by L by R whole square. L by R is called the slenderness ratio of the column. If L by R is bigger, then our stress, the critical stress, will be smaller. So in other words, we will always be interested in the radius of gyration, which will maximize our L by R square. As an example, we can draw our P by A and L by R for a steel having proportional stress equal to 200 megapascal. Plugging the values, we have 200 into 10 raised to power 9 pascals for steel modulus of elasticity and 200 megapascal proportional limit, and that gives us the slenderness ratio approximately equal to 100. So this tells us that the Euler equation is valid for slenderness ratio greater than 100 in case of steel having proportional limit 200 megapascals. So below this value, we can't use the Euler equation. Before applying Euler formula on examples, let us discuss one important aspect related to the use of this formula. As we said that P critical is equal to n square ei pi square by le square, where n is the length of half sine period. So as we know from our previous derivation that the column will assume the shape of half sine wave if both ends of the column are pinned. If we restrain it in the middle, then it will assume twice the length of half sine wave. In other words, we would have a full sine wave. Similarly, if it is restrained in two direction, then we will have one full sine wave and a half sine wave. So n control the length of the half sine wave. E is the modulus of elasticity for the material. I is the least moment of inertia for the column's cross-sectional area. Then we have pi square, divided by effective length LE, which is the unsupported length of the column whose ends are pinned. Important thing to appreciate over here is that the smallest value of P critical is obtained when N is made equal to 1. So the critical load will come out to be EI pi square by LE square. This load is sometimes referred to as Euler load. In the examples, we will try to use this equation and find out our critical column load. Since we have put n equal to 1, therefore the effective length will be equal to half sine wave length. In other words, if the column is unrestrained and pinned, then according to this formula, the effective length will be the height of the full column. However, if the column is restrained in the middle, then the effective length will be equal to half the height of the column. So n will be equal to 1 and effective length will be equal to half the height of the column. If the column is restrained in two regions between the supports, then effective length will be equal to the 1/3 of the column height, assuming that the unrestrained length is equal. Therefore, we can say that this formula will assume the effective length corresponding to the deflected column making half sine wave. Now let us discuss these examples in order to further clarify the concepts. The first example is asking to work out the critical load. We are given a section W 6/15 C steel column, which is 24 feet long and is fixed at its end as shown in the figure. Its load carrying capacity is increased by bracing it about the YY weak axis using the struts that are assumed to be pin connected to the mid height. Determine the load it can support so that the column does not buckle nor the material exceed the yield strength. After that, we are given the modulus of elasticity of steel and the yield strength of steel. The important thing to appreciate is the units. We have to be very careful in using this formula and making sure that the units are consistent in the numerator and denominator. In this equation, we have to find the minimum moment of inertia and the effective length. As we can see, the column has got two axes, or in other words, there are two potential axes about which the column can buckle. The column is of I-shaped, as we know the W section is the standard form for an I shape. In the case of I shape, the moment of inertia about x-axis is bigger than the moment of inertia about y-axis. Thus, x-axis is called major axis and y-axis is called minor axis in the case of I section. Please note that the buckling about the major axis will have full length, which is 24 feet available. On the other hand, the buckling about the minor axis will only have half the height of the column available. In other words, about the major axis, we have the full height of the column available to make half sine wave. In the case of minor axis, we have only half the height of the column available to make a half sine wave. In the case of major axis buckling, we have to plug the value I max and take LE corresponding to the fixed end condition. So as per this table, the fixed ends will have half the length available to buckle. As we can see over here, in case of fixed end, there is only the length 0.5 L available to assume half sine wave. So effective length will be equal to 0.5 times 24, which gives us 12 feet, and I max and I min can be obtained from a table. So the section W6 into 15 is shown over here. As we can see, the moment of inertia about the x-axis is 29.1 inch 4, and about y-axis is 9.32 inch 4. So that clearly tells us that the moment of inertia about the major axis is almost 3 times that of the minor axis. So this distinction has to be appreciated in the column analysis. So we can get the value from this type of tables. Normally, one can find such tables in code of practices. If one is looking at steel code of practices, they issue such sort of tables. Fabricators or other people in industry also have got their own tables like this one. Now we can work out our critical load in both the major and the minor axes. In case of major axis, we have pi square E, so pi square times 29 into 10 raised to the power 3 ksi. Then Ix is 29.1 inch 4 divided by KLX whole square. So K, as we said, was 144 inch. So that is squared in the denominator, and we get 401.7 kips. Similarly, we can do the same exercise for minor axis, and pi square E will stay the same, I will be reduced, and similarly, KL about the minor axis will be reduced. Now, please note that the KL about the minor axis is for the case when we have got one end fixed and another one pinned. Remembering that we are considering only the half sine wave, so the half sine wave will be in the depth of 12 feet. So K time L for one end fixed and the other hinged is 0.7 L, and that can be easily taken. 0.7 times 12 will give us 8.4 feet, and that is converted into inches. As I said, that in the case of column analysis, it is important to appreciate that the units are consistent. So we have got the numerator and denominator in inches. Once the critical load is found, then the one which will give us the minimum will be governing, and the critical load about the minor axis is governing in this case, and which is 262.5 kip. 262.5 kip can be divided by area, and we can get the critical stress. We can do the same type of exercise by using the slenderness ratio. So we discussed that our critical stress is E pi square by slenderness ratio whole square. This L is effective length, which is equal to K times the length of the deflected column in the shape of half sine wave. So KL by R about the major axis is given 56.2, and KL by R about the minor axis comes out to be 69. Now in this case, clearly the maximum slenderness ratio will be governing this equation. So the maximum slenderness ratio is corresponding to the minor axis, and that is governing. So hence, it's up to us whether we want to work out the critical load from the slenderness ratio or we work out from the applied load. Now, in this example, reference is given to Appendix B, where based on the slenderness ratio, we can find out the critical load. So let us go to Appendix B. And in the case of Appendix B, we can visit the same appendix and get our constants. So from these both equations, we have got the y-axis or the minor axis being susceptible to buckling. Now, in this another question, we are given an aluminium column that is fixed at the bottom and braced at its top by cables so as to prevent movement at the top along the x-axis. About the minor axis, it is pinned, and about the major axis, it's free. So free from the top and fixed at the bottom in the case of major axis buckling, and in case of minor axis, it is pinned at the top and fixed at the bottom. So those are the end conditions. We are given all the other properties. We are also given a factor of safety. This factor of safety has to be divided by the critical stress. So it's similar to whatever we had in the previous question. Only thing is that when we get the critical stress, we have to divide it further by a factor of safety of 3 in order to make that stress allowable stress. Or in other words, we shouldn't exceed the load which will cause more than that allowable stress. So again, it's the same story. We have got about the major axis, a free end and a fixed end. Since this is a cantilever, about the major axis at the top and fixed at the bottom, so this is a clearly the case having k is equal to 2. So in order to make a half sine wave, we have to have effective length equal to 2L, and that is why k is equal to 2 in the case of major axis buckling length. And about the y axis or minor axis buckling, k is equal to 0.7, so that is 0.7 times 5. So k is equal to 0.7 times 5. This time the minor axis support conditions are fixed and pinned, so we have this fixed and pinned case, which in which case effective length is 0.7L and k is taken as 0.7. So plugging the values, and we get P critical 1.31 meganewton in the case of minor axis load, and the major axis critical load is 424 kilonewton. So clearly this time the major axis is governing. Now this load can be either divided by factor of safety to make it an allowable load, or we can convert it into critical stress and divide that by factor of safety in order to make that as an allowable stress. So allowable means that the structure should not go beyond that load, or the applied load should not go beyond that particular limit. Now finally, a very brief discussion on intermediate columns. Now, in our previous discussion, we have shown long columns that can be treated by using Euler equation. It is important to note that the Euler formula is applicable in the case when slenderness ratio is larger than the value at which the average stress reaches the proportional limit. So as we can see over here, when the average stress reaches the proportional limit, then the Euler formula can be applied. Before that, Euler formula cannot be applied. In this example, we can see that our L by R, or the slenderness ratio, is approximately equal to 100. Euler formula is not valid for smaller slenderness ratio, as we can see over here. Over here, we need to define a short column. A short column is the one whose length does not exceed 10 times the least lateral dimension. The upper limit of slenderness ratio at about 30. So remembering that this example was done for a pinned support condition, if we go to the point where the slenderness ratio is about 30, at that point we can treat the column as a short column. So every column having slenderness ratio between 0 and 30 will be classed as a short column. So let us check this full graph. So we have again the short column limit, which we said is 30. This example is for a steel section having a proportional limit equal to 200 megapascal, modulus of elasticity equal to 200 into 10 raised to power 9 pascals, and the support conditions pinned. So in the case of short columns, there is no buckling, and we can use simply stress is equal to P by A. Simple axial stress will actually give us the failure stresses in the column. Thus, between the short range and the long range, there is a region which can be called as an intermediate columns. So columns having slenderness ratio between 30 and 100 for the conditions which we discussed, our column can be classed as an intermediate column. It is important to note that in the case of a short column, the limiting stress is not taken equal to proportional limit, but it is taken equal to the yield limit. So in order to find out failure load in the column, we just use the yield stress and multiply that with the column cross section, and we can get the critical load which will cause the column to crush. Remembering that the short columns will crush, the long columns will buckle, and the intermediate columns will have both buckling and crushing on pro rata basis. So proportionately, they would crush and they would buckle at the same time. Therefore, in the case of short column, we can say that instead of going to proportional limit, we can apply additional load and go to the yield point, which is around about 280 megapascal for this particular reference column. Now we know that the short column crushing stress can be found by stress is equal to P by A, and for the long column, we can use the Euler curve. What we don't know is the critical load for the intermediate columns. Various methods have been proposed for bridging the gap between the short column range and the long column range. However, none of them has been accepted universally for the intermediate columns. This is because of their departure from the stress-strain relationship when the stresses exceeds the proportional limit, and partly because of their indeterminate mixture of direct and flexural stresses. Hence, different codes of practices actually gives us empirical formulas for indeterminate columns. The empirical formulas are commonly given in the steel code of practices because this sort of issue is more common in steel than reinforced concrete. Steel, being a slender material, is more susceptible to buckling as compared to reinforced concrete. In one of the proposed method, the Euler formula is extended to the intermediate column region, which are stressed above the proportional limit. And this is done by replacing the constant E in the Euler formula by the so-called ET, or the tangent modulus. This is called tangent modulus theory. So the same critical load is used, but instead of modulus of elasticity, E corresponds, a tangent modulus is used. Remembering that modulus of elasticity is the slope of stress-strain curve when the applied load is within the elastic range. Since the applied load has gone beyond elastic range, therefore a reduced modulus is used, and that modulus is called tangent modulus. Empirical formulas are available to find out the tangent modulus. Since we can see that this is a parabolic curve, so we can find the tangent corresponding to this parabolic curve, and that can be used in the Euler equation to get the critical load. Now, this is a figure from AISC, American Institute of Steel Corporation manual. This figure is similar to what we have seen over here. In this figure, we have again a region of elastic buckling and a region of inelastic buckling. In this figure, we have got the Euler buckling region, and then we have got the region before Euler buckling. It is important to note that in practice, it is not possible to get the load equal to the one given by Euler buckling even for the long columns. The reason is that in the case of steel columns, we can have geometric imperfections and residual stresses induced in the structure before application of any load. A steel I section column will have some internal stresses already applied on it during the process of its fabrication. And it might not be fully straight. It might have some imperfection which would make it a bit crooked. That's why it is not possible to get exactly the same buckling curve as proposed by Euler. The code of practice normally gives another curve which actually takes these effects into account and gives a modified curve. In the case of long columns, we have the equation of this curve as 0.877 Fe, and in the case of region before long column maximum limit, the equation is 0.658 raised to the power Fy by Fe, everything in bracket times Fy. This curve is drawn between the slenderness ratio and the critical stress. FCR is the critical stress. Now let us see what these variables are. P critical is the Euler buckling load. F critical or stress critical, which we discussed, is P critical by A. This P critical has to be multiplied by some reduction factor. So in our example, we divided our critical load by a factor of safety which is greater than 1. The code either asks to divide by a factor of safety or multiply a factor which is less than 1. These two parts of the code curve are shown over here. If we have the slenderness ratio less than 4.71 square root of E by capital Fy, where Fy is the yield stress in KSI, then we can use F critical equal to 0.658 raised to the power Fy by Fe, everything multiplied with Fy in bracket multiplied by Fy. Fy is the yield stress in KSI. Similarly, if the slenderness ratio is greater than this value, then F critical is equal to 0.877 Fe. Fe is equal to elastic Euler buckling stress. So Fe is actually equal to P critical by A. Le is the effective length as we discussed. The code also gives approximate values of effective length factor K, where we have a theoretical value of K as we discussed for different support conditions. So if both ends are fixed, K is 0.5. If one end fixed, one pinned, it's 0.7, and so on and so forth. Then the code gives a recommended value which is less than the actual value. So in the case of both end fixed, instead of taking 0.5, the code says we can take 0.65. So we have a recommended value of K which are bigger than the theoretical K value. So for example, in the case of both and fixed column, the recommended value of K is 0.65. In the case of fixed and pinned, the recommended value of the code is 0.8. It must be noted that the same formulas we discussed in our mechanics, they appear in the code of practices. However, the code of practices apply some additional factors on it to make it more conservative or to make these equations more practical. Like for example, the column allowable load is multiplied by a factor which is less than 1. So that is to add more conservatism because of uncertainties in the design. Then the code add an additional conservatism by enhancing the value of k. We can see if we take the value of k bigger, that will give us a smaller critical load.